test field methods for extracting mean field coefficients, of course, mainly in famous alpha from simulations. And I have to make two remarks at the beginning. So I must warn you, this will probably not be a very inspiring talk, because I will not present a fancy movie or mesmerizing astronomical photographs. Instead, it will go through mathematical stuff, will be quite dusty and boring maybe. And I can only beg you to follow me into this tunnel of work, where at the end maybe the chances that you see some tiny light of hope that what you have heard will be of benefit for your work. And the second is, this is a school, and you may legitimately expect that what is presented here is some sort of well-confirmed, sedimented knowledge, which is in the textbook, or should be in the textbook, or will be next time. This is not completely true for my talk. Only for the first part, one can say that these results are sufficiently confirmed. The second part is quite recent and experimental, and I would like to ask you to hear and to take this up with caution, and to bring forth any doubts or criticism you have. Of course, all the lecture through, but especially in the second part. Now let us have a short look onto the outline. Because I said this is maybe a dusty and boring stuff, I owe you a good motivation why we should be concerned about test field methods at all. And that's why the first point is motivation. And then I will go on to some, very brief, to some conventions and terms, definitions. And then a major part will be the test field method as established up to now, which applies safely for purely hydrodynamic background turbulence only. And I will give here some the basics and some examples. And then at last, or almost at last, the second major part, the new extension of this method to magnetohydrodynamics background turbulence, where the background, I come to this term, is no longer defined by velocity fluctuation alone, but by a velocity and a magnetic field fluctuation. Again, those examples, and a brief outlook on what could be done further at the end. Yeah, starting with motivation, there are several layers of motivation conceivable for that. One is from within. So mean field theory has been elaborated for more than 40 years now, and on this stage then any theory and the theorists in it have some interests of their own to extend the theory, to cover more cases, to be more general, to be more reliable. And that's why there are some of what I call the inner needs of the mean field theory. It comes first from some restriction of the analytic method. You know, you have heard already during the school a lot about it, that analytic methods were at the beginning, and they were really successful for a long time, but they had their specific restrictions. And one of these is that they are only feasible, or they are assumed to be feasible, to be more precise, to work together with closure methods, or closure assumptions. For instance, the famous second-order correlation approximation, SOCA, which you have heard about already too, which means simply that if F and G are fluctuating fields, some fields may be velocity, magnetic field, and something like that, then the fluctuations of this product, F times G, will be neglected. The average of this product is usually that's what we are interested in, for instance, the mean electromotive force, but the fluctuations play a role in the governing equations, but SOCA says we neglect them simply, and this leads to considerable simplifications in the work. And what is the advantage of this closure assumption? We know about sufficient conditions for its applicability. Another closure is the so-called Tau approximation, where third-order correlations are brought down or are related to second-order correlations. For instance, if you have an evolution equation for a second-order correlator, something like that, And on the right-hand side, you have some third-order correlators, like these. Then these are substituted by such an assumption, saying that if there would be nothing else on the right-hand side than these two guys, then it is supposed that the correlator decays. So this is just expressed by this minus and this tau as a characteristic time of this decay. The problem with this approximation, although a lot of work has been done with it, and one can really say successful work, the problem is that we are not sure about the applicability conditions for it. So we are not in the comfortable situation like in soccer where we can say these are at least sufficient conditions. And it's uncertain to what extent the results of this method really overlap with the results of soccer. Well, they should, because the tau approximation is thought to be something which goes beyond soccer. So we should see an overlap, but we don't see it completely or satisfactorily. Then what I said, that analytic methods are feasible only with closure methods, closure assumptions. This is not quite true, because, and you have probably this known already by Karl-Heinz Redler, that we can go even in an analytic calculation up to arbitrary high correlations. And this is done by such an iterative procedure, starting with the soccer level, indicated by 1, and having here the mean field on the right-hand side, and then using these results already on the right-hand side here, going to higher and higher contributions to the fluctuating field B. And it is even proved mathematically that this procedure is convergent, but of course you see immediately this is a cumbersome piece of work. But there's another thing connected with both approaches, the closure approaches and this iterative approach. In any case, at the end, if you want to get numbers out of your formulae, you need to know something about the correlations. Mainly, of course, the second-order correlations, but higher order correlations too, if you employ this procedure. And then this is the point where, again, or where necessarily some ansatz have to be done for the correlation functions, which at the end describe the spatial or temporal, or if you have the frequencies and wave number space, the k and omega dependence of the correlation functions. And where do we know that from? What is the reasonable ansatz or not? This is really not very safe ground. So then it is probably a very reasonable idea to say, okay, if we don't know these correlations, we have powerful computers with thousands of processors meanwhile, and soon there will be maybe 1 million. So why not taking out correlations from simulations? Sounds not so bad, but then if one is really consistent, one would say, yeah, why then not immediately taking out the mean field coefficients from the simulations, instead of doing analytical work, which at the end is lacking something, which we take from a numerical simulation. We would then do the whole job immediately, starting from the simulations. And this leads to the test field methods. Another layer of motivation comes from above, from the sky, and from the importance of theory, because mean field theory on its own is important for the theorists, and that's it. But predicting something with its help, say the next the next solar cycles, is of interest not only for the theorists but for many people. In that sense, it is a motivation from above if we speak about solar cycle modeling, and one has immediately conceived that this is a really ambitious project, because there is a need, or a model is wanted, which reproduces essentially all the observations that we have about the sun. Of course, anyway, the 22-year cycles has to be reproduced. Then it's a variability in amplitude and period. It's just what we are interested in, how strong or how weak will be the next cycle. And what about the occurrence of active regions, of sunspots? Do they occur on the right latitude? Do they migrate in the right direction towards the equator? Furthermore, we have an interplay which has to be modeled too with the differential rotation, which we know is an essential ingredient of the dynamo, but the dynamo, of course, acts back on it. And further on, meridional circulation, which in some models, play a really crucial role. And for instance, torsional oscillations, which we are believed to be tightly correlated with the magnetic cycle. And at the end, something like the long-term modulation, which is connected with the term the grand minima. The challenges which come out of this sort of program for the mean field dynamo theory are the following. With respect to the Sun, we are quite certain, meanwhile, that there is a primary MHD turbulence, that is, there is a small-scale dynamo, which means that already if there's no mean field, we have nevertheless already magnetic fields, namely small-scale ones, which is not so obvious at the moment that this is a relevant aspect, but it really changes mean field theory as up to now, one must even say, the major part of work done within this theory has been done on the assumption that the primary turbulence, the turbulence without the mean field, is hydrodynamic. Then we have anyway high magnetic Reynolds number, like always in astrophysics, or almost always in astrophysics, which is, a complication for analytic methods. We need to model the back reaction on the flow in the framework of the mean field dynamo model. And we have even to worry about something like non-locality. So is it really a good idea to model the mean electromotive force with help of, or to express the mean electromotive force with the help of the values of the mean field at the same spot? Or isn't there a need to include in the expression of the mean electromotive force values of the mean field at other places? So, for instance, if you think about the Babcock-Leiten mechanism, there you have an alpha effect, which employs a magnetic field which is not at the place where this electromotive force is employed, but comes from the bottom of the convection zone. Yeah. This program with respect to mean field dynamo theory badly needs these two expressions, the mean electromotive force and the mean force, so ponderomotoric force, both as expressed by the mean magnetic field and the mean flow. And okay, this looks nice, and you might say, if we don't have any plans for this afternoon, then let's derive these. But what does this really mean? For this purpose, I want to make, for the moment only, a few simplifying assumptions. Let us assume a primary turbulence which is isotropic. Then consider only mean fields which are 1D, so we have averages over two spatial dimensions. Let us neglect all higher order spatial derivatives and all temporal derivatives of B in the mean electromotive force. And let us assume that the mean current is in some sense weak, so that the dependence of the mean electromotive force on the modulus of the current density, the mean current density, is only linear, but the dependence on the mean magnetic field arbitrary. So if we do these assumptions and only ask for the structure of the mean electromotive force which comes out from that, and which at the same time defines what functions has to be determined, then we get the following. Oh, sorry, I forgot this one. To assume this assumption that if the mean field acts back on the turbulence, that the turbulence feels this back reaction immediately without any delay, which is of course an artificial assumption. Then the result by structure only is the following. You see here the electromotive force expressed at the end by 5 functions, which are here colored red. And the notation is somewhat arbitrary because formally one would tend to say, okay, the coefficients would go here as a factor of B, and here again as a factor of B, and those which come as a factor of the mean current density here and here. The first should be named something like alpha, and the second should be named something like beta, or turbulence diffusivity. But this is not so clear, because if you consider this equation energetically, then you will see that not all terms inside, not all terms named alpha really have the potential to generate field, and not all terms named beta are really dissipative. So this is only a formal notation.
Sorry, yes.
Yeah.
Could you please explain again what is meant by 1D mean fields in there?
It means, for simplicity, say we average over all x and y, and the mean quantities which come out are only dependent on z. That's the definition of our mean.
So depends on one variable. Dependence on one variable.
On one spatial variable. It is only for the purpose of this consideration at the moment. But I will come back to that sort of average. Yeah, and this is the task, and we need to know these functions as functions of the modulus of the mean field. And of course they are determined by properties of the original, uninfluenced by the mean field turbulences, which could both be velocity and magnetic field fluctuations. So then I would give this comment. You see, I'm pretty skeptic that there's any chance to do that with analytic means. Next level or layer of motivations is something or sometimes in science you get motivation even from anger, even from being attacked, or even from a controversy. And in this case, there's sometimes it happened that the outcomes of the mean field theory, or especially alpha effect, has been challenged by people who employ the so-called imposed field method, with conclusions like, oh, the alpha effect is not really existent, and mean field theory breaks down and cannot describe something, and so on. And then, because this is connected with this term imposed field method, let us first briefly look what this means. This is the first method used for deriving alpha from simulations, and it means to add an imposed uniform field to a certain MHD simulations, which provides you the fluctuating fields. Then to calculate the mean electromotive force, which is can easily be done by from the results of the simulation, and then calculate this quantity, which turns out to be the component of the alpha tensor with respect to the parallel direction, the direction parallel to the field. And this method has, of course, as any method, some limitations. The first is that you usually can get only alpha, and because this is a uniform field, and all other effects are connected with a derivative of the field. So I'm not sure whether there were any attempts to do something like that for deriving eta tensor or diffusivity tensor. I don't think so. And more important even, the measurement is invasive. So if you have your original system creating your turbulences and put in the mean field, means of course to disturb the system. It's no longer the same. And what you measure are properties of the disturbed fluctuation, not of the original ones. This might be a minor inconvenience if the imposed field is very, very low, but it introduces some sort of uncertainty. Anyway.
So, yes, but you can measure eta, right, this way, if you introduce current of varying B,
yeah, a varying
and
B.
look at the gradients, right?
Yeah, but then it's not so longer so clear what this average then should mean. You know. Maybe there were attempts to do that, but I think they were not successful. I'm not sure.
No, not successful, I think so.
Yeah.
I don't understand how it is invasive as long as the little b you written is linear in B imposed.
Yeah, that's true. That's another problem. The amplitude drops out here. But if you set in the mean fields in your MHD simulation, in the full equations, then of course it creates an effect. So
if the interaction parameter is small, no.
Pardon?
If the interaction parameter is small, it doesn't create.
If the amplitude goes to zero, yes, you're right.
Okay.
Yeah, that's true. But how to say it exactly? if you want to go beyond kinematics with this method and to derive something like quenching functions, then your problem starts. Yeah. Okay, and the other thing is there are not only limitations, which one should of course be aware of, but pitfalls, and sometimes people really tumble into these pits. Namely, that in addition to the imposed magnetic field, some other mean field could occur coming from a dynamo mechanism in your MHD simulation. And if you're not aware of that, you still employ the imposed field at this point, forgetting about the part of the mean field which is of the mean EMF, which is really coming from the dynamo-generated mean field. So this really, of course, creates a wrong result. And the other thing is that sometimes people even employed an averaging in here, this average, in a situation where alpha is essentially space dependent and averaging out in this way a major ingredient of alpha. Okay, so controversy sometimes creates motivation. And now briefly, let me come to some terms and convention. This is mainly recalling things you already have heard during the school. Yeah, terms mean, this I think quite clear, that it's fluctuating. I will speak about fluctuating fields in a very general sense, so it doesn't mean they are that they are depending on time. It simply means they are not means. Everything what is not a mean, what is not an average, will be denoted in my talk by fluctuating field. So it's simply a convention. Don't worry about it. You may replace this term, but I use this one. And the operation is as usual indicated by this overbar. Then this means we split off any quantity f into a mean and fluctuating part, with the fluctuating parts are usually denoted by lowercase letters. And sometimes the extraction of the fluctuations is denoted with a prime if this is a more complex expression. So the prime means strip off the mean part and leave the fluctuating part. Then the terms, it's a sort of caveat. So what is about small and large scale dynamos? Are these terms synonymous to these? So is of crossing, of course. So is any mean field a large scale field, and any fluctuating field a small scale field? No, it's not. It depends on the average whether this is true or not. Consider, for instance, as the mean operation, the averaging of a phi. If you had a cylindrical symmetric geometry or a spherical symmetric geometry, then those kinds of this kind of average is convenient as usual. Goes back to Braginski. I think he was the first who employed that. And then, of course, the m equals 0 modes are mean fields, and all the other modes with m unequal to 0 are fluctuating fields, of course. But if you now would identify these modes with large scale and these modes with small scale, you would run into how to say, unreasonable conclusion. Because if you consider 3 decay modes of B, then there is a degeneration with respect to M. So with one and the same order of a spherical harmonic and the order of the radial eigenfunction of the decay operator, you get the same decay rates independent of M. So it would not be appropriate to say that the M equals 0 mode is large scale and the M unequals 0 mode is small scale, although they have the same decay rates. If they have the same decay rate, they necessarily have to have the same scale. So be careful with these terms. And yeah.
Perhaps better not to use them, right?
Pardon?
Better perhaps not to use them.
Especially, or except you have a well-defined average where it is clear that all the fluctuating fields need to be small scale. Then why not use them?
But otherwise, mean and fluctuating are
yeah, this is what I prefer.
Perfectly precise terms. Which as soon as you define your average,
yeah,
it's
yeah,
exact,
it's would
no
be,
confusion arises.
Would be my preference. Yeah. Yeah. What is referred to with background turbulence? This simply means the turbulence we see if there is no mean magnetic field. for primary turbulence. The turbulence which is there before the magnetic field starts to grow, before it starts to have any influence. In opposition to actual turbulence, which means the turbulence which is already influenced with the mean field. And I will need for that the subscript 0 for background and B for those parts of a field which depends on the mean field. So for instance here we have fluctuating velocity field and fluctuating magnetic field can be split off into two parts each. And these parts UB and BB have the property that they vanish together with the mean field. That's the definition. And the other parts have the property that they are still living if the mean field is 0.
You can also have, say, U sub small b, right?
You have that. What do you mean?
Yeah, I understand. Yeah, you could, but I haven't considered that.
In
principle, yes. But I haven't considered that. So on the level of my considerations, I have either the fluctuations somehow created together of U and B, or if there is an MHD turbulence at the beginning, a primary MHD turbulence, so not worrying about how they were created, or I have only one of these two. But I don't consider how first a small scale U could be there and then a small scale B could emerge, which is a legitimate question in the case of a small scale dynamo, of course. But I don't consider this process. And then abbreviation, so you have already heard SOCA and DNS. It has nothing to do with genetics, but with direct numerical simulation. Yeah, next section, I call it feet on firm ground because this is really the part where we have certainty that the results are reasonable. This is referring to purely hydrodynamic background turbulence. Here's it again in notation. So the B0 is 0. And all the B, all magnetic fluctuations, are due to the mean magnetic field. That's an important point to remember, to memorize. Further on, I assume at this moment that the velocity U is prescribed, then the mean electromotive force, which could be split off in two parts, E0 and EB2, is of course 0. Because E0 is the average of U0 cross B0, and if it's B0 is 0, then we get 0 here. So all the mean electromotive force is emerging due to the action of a mean field. This is written here. E is equal to, sorry, here the overbar is missing. E is equal to EB in this case. So now we have the well-known equations. The full induction equation, where I use this abbreviation, simply script E for U cross B. Then the average of it, which then contains the average of this quantity, the mean electromotive force. And by subtraction of these two equations, we get the equation for the fluctuations. Nothing new for you, this is quite easy to get. And we may readily give a solution, a general solution for that in terms of Green's function, which in the general case, if we don't employ SOCA, depends on the velocity fluctuations, of course, on the mean flow too. Yeah, some remarks to this equation. Obviously, B is now a functional of these three quantities. It's clear why. You see this from the right-hand side readily. But what is maybe, what is not surprising, but is important. It is an arbitrary function of these quantities, but it's not an arbitrary, but instead linear and homogeneous functional of the mean electric field, mean magnetic field. You see this immediately. If you scale the mean field with a factor, then the fluctuation will scale by the same factor. Further, then as a consequence, the mean electromotive force, which results from multiplying B by U, essentially, is again a linear and homogeneous functional in the mean field. The same story with a scaling factor.
Excuse me, you're assuming that the velocity
Sorry?
field is given.
At the moment I assume that.
Unchanged.
And the moment I assume it is simply given.
Okay. Otherwise,
I will relax. I will relax that.
All right.
But at the moment not. If we make an ansatz of this sort, which you are quite familiar with, then it's again clear, because this is just a linear and homogeneous expression in the mean field, that A and B are only functions of the velocities. That is, in other terms, these tensors, not A and B, alpha and beta. Alpha and beta reflect correlation properties of the flow, not properties of the mean field at all. Only properties of the flow. To be very precise, one has to say they reflect also the magnetic diffusivity and the magnetic boundary conditions, because these quantities enter the Green's function. But it's not important for us. So this means, further, that if we remember the preceding slide, maybe I should go back. You remember this equation, then for figuring out alpha and beta, which reflect properties of the flow, it is without any relevance what mean field is put in here.
Yes, why you say that? You dependence on alpha and beta and eta you allow, right? Yes.
Oh, yeah.
Okay. So I misread
But to be precise, it's something a bit more than only the correlation properties of the flow. But it's not relevant for us at the moment, or throughout this talk. Now we can easily define the test field method to be a procedure of the following steps. First, solve the equation we have just have seen, but now I have put this index k here at the solution and at the mean field, and it means that this should be done for a series of fields, not only for one field, one mean field, but for a whole series of these mean fields, which we now call test fields. And then for each k, of course, you get some lowercase pk, fluctuating field pk. Calculate for every k, for each k, a mean electromotive force, and now obtain the components of the alpha and beta tensors by inverting these equations, which is now, of course, forming a system of equations because k is running. And the solution, in the sense of the solution of this linear system of equations, of course, is unique if the number of test fields is chosen appropriately. So, of course, it must be big enough to be able to figure out all the components which are in these tensors here, which I have not specified at the moment. And in addition, of course, the test fields have to be chosen sufficiently independent. Otherwise, you would end up with a degenerate coefficient matrix in this linear equation system of equations. Some remarks to that. I repeated the equation here, the test equation, we call it. In deriving this equation, the divergence freeness of the mean field was not used. So it seems to be not important to have this property really in the test field procedure. Then the right-hand side, as usual in partial differential equations, is not restricted by any boundary conditions at all. Boundary conditions restrict the solution, not the right-hand side. So this doesn't mean, in fact, that magnetic boundary conditions are not relevant for the test fields.
What defines the left-hand side and right-hand side in this equation?
Pardon?
What defines which terms end up on which side of the...
Right-hand side is this one.
Homogeneous.
It's
Inhomogeneous term.
Inhomogeneity.
Oh, okay.
The inhomogeneity. Because this is homogeneous. You see, every part contains the bk, but the right-hand side is inhomogeneous. Yeah. So that it means there's in fact no restriction of the test fields by any boundary condition. And for the existence of solutions, we have only these very weak properties to satisfy on the right-hand side. So this allows for a broad range of test fields, in fact.
But Matthias, you can make an effort to be very silly and choose such form of the test field,
Yeah.
which will contradict, be almost inconsistent with the boundary condition for B small.
Yeah, you may do so.
Boundary layers on the boundary, so something crazy. If you do something crazy,
You
then
may
it can
do
be a
so.
problem, right?
Only numerically, not mathematically. If you are sure that the results, so alpha and beta, which come out from the procedure at the end, don't depend on the test field. You have to make it sure. Then it doesn't matter. You may run into numerical difficulties, but not into mathematical. So yeah, this maybe just now the point. To what extent is BK really arbitrary then? For sure, with respect to its strength or amplitude. So because it is clear that the amplitude drops out again. But what about the geometry? The geometry wouldn't play any role if this ansatz we have made were complete. But in general it is not. Because we know this is a truncated Taylor series, and there should be, beyond that point, further contributions with higher spatial derivatives, temporal derivatives, mixed derivatives, and so on. And it's even not clear whether this Taylor series converges. So it is a dangerous thing to postulate that this would be a complete ansatz. And if so, if this is not complete, we can say that the geometry of the test fields is only arbitrary within the class of fields for which the ansatz, this ansatz, is indeed valid. So, if we know this ansatz is only valid if we consider stationary fields which are at most linearly depending on spatial coordinates, then these test fields are arbitrary in that sense that they have to belong to this class. They have to be stationary and linearly depending on the spatial coordinates, but otherwise they are arbitrary. Yeah, now...
Can I ask a quick
yeah.
question? There was some controversy about whether it's important if higher derivatives that don't show up in the expansion are zero or not. Is it discarding the contribution from these terms or having those as a pollution in the coefficients that you measure, or what would be the difference?
If you don't obey this rule that the test fields should belong to this class of fields, then you pollute your coefficients. Yeah, that's true.
So if I choose sinusoidal fields where there exists higher order,
you don't get any longer the usual alpha. That has to be taken into account.
So I have to assume that these higher order contributions are small.
If you can assume that, but we know from examples in the spherical animal that this need not to be true.
You mentioned non-locality, maybe. Briefly.
Yeah, it is connected with locality. Yeah, can be connected. So now all this story for one-dimensional averages. So we have, say, average over x and y, and the mean fields are only z-dependent, as I already said. The consequences of that are that the gradient tensor of B is completely representable by components of the mean current. Sorry, here's an overbar missing. Sorry for that. Then the beta tensor, which was connected with the derivative tensor of the mean field, which was rank 3, now degenerates to rank 2, and we name it an eta from this point on. And the z component of the mean field is constant, and the z component of the mean electromotive force does not influence the field at all. So we can restrict ourselves to an ansatz for the mean electromotive force of this kind. You see here this vector eta instead of beta, which is now connected with the mean current density and no longer with the derivative tensor. And here we are only interested in the components for I and j 1 and 2, and not the 3 with I or j equal 3 components of this tensor. They don't play a role in the mean field models. That is, in total, we have 8 tensor components, 4 here and 4 here. And one test case, that means one test field yields one electromotive force. Each of these vectors has 2 components, so with one test case, we get 2 unknowns, and in total we need 4 test fields. And the usual choices are, I'm not aware that something was done beyond that even, are polynomial test fields or harmonic test fields, because coming to this point. Or, yeah, to your point too. Let us first consider polynomial test fields. It could be, for instance, constant fields like that, so where either the x or y component is simply a constant, and another sort where either the x, it's expressed by this delta operator, either the delta symbol, where either the x or y component is proportional to z simply, and then the mean current is constant. And in this case, we can have a 2-stage procedure. First, calculate alpha by this rule, and if you're fine with that, you may stop, if you're not interested in anything more. But if you want to know the eta components, then you may proceed using this result, which you already know at this place, and where this explicit formula you then will get then the divisivity tensor components. I only mentioned that this really creates a big trouble for periodic boundary conditions in a numerical setup, but not necessarily, for instance, in the spherical models which Martin Finner considered. There was not really a problem there. Harmonic test fields are notated in this way, that again, either the x or the y component is either depending by of z by a cosine or by a sine. And now you may, of course, ask, k is a parameter in it, so the results, what we figure out, alpha and eta, will depend on k. So what does it mean? It means, first, that these k-dependent tensors are have no longer the same usual familiar meaning as the alpha effect, as we discussed it up to now. Instead, they comprise a lot of contributions to the Taylor series, each of them. In fact, infinitely many. And in other terms, k-depending tensors of this style mean that you have no longer a local relationship between the mean electromotive force and the mean field. But I don't want to go into detail at this place. Yeah. Here again, we can give a right.
Okay, so what you just said seems to me, don't even try using such harmonic fields.
You may try if you interpret the result correctly. You have to, for instance, should apply it in a situation where it is the right k. For instance, if you know that the mean field will have this k for which you have calculated tensors, then you're fine. If you don't know that, you in fact had to employ the k-dependent things, and this means in physical space you have to evaluate convolution integers. That's the make it true. And yeah, well, you may imagine that considering these systems, then the harmonic ansatz, harmonic test fields, we have 2 decoupled systems of equations, and finally arrive at these explicit expressions for the. Oh, sorry. Forget about this. This should not be here. This is interesting for the moment. And these explicit formulae for alpha and eta tensor components, and the matrix here is already the inverted coefficient matrix of the former systems, with the simple structure of a rotation matrix. Yeah, some comments on applications without going into detail. The method has been applied to forced isotropic turbulence. You know that one can mimic real turbulence by applying a forcing function, a ponderometric force, which has random properties, changing, for instance, plane waves, which are changing their wave number and even amplitude from time step to time step, and they create something which really looks similar to physical turbulences. here alpha and eta tensors, of course, has been determined. The shear current effect and the omega cross J effect has been studied for non-helical turbulence, where you don't have alpha, but where you can nevertheless have, as a consequence of the shear current effect, still have a dynamo. And further, what already has been discussed, the wave number and frequency dependence of alpha and eta, which then comes to non-local, non-instantaneous formulations. Further, it has been applied to regular flows, like, of course, the Roberts flow, which is always something like a benchmark, or anyway, a flow for which a lot of analytical results are known and which are very well confirmed and so on. That's why it's usually done always with the Roberts flow too, with the Galloway-Proctor flow and then a contact flow. And last but not least, this was Petrie's work mainly. It has been done for rotating and shearing convection with a view to applications to the sun. And here we have inhomogeneous alpha and eta profiles, because you may imagine that the convection in the convection zone of the sun is not a homogeneous thing, but has for sure a Z dependence or a depth dependence. Yeah. Now, let us look for the much more interesting thing. What about if the mean magnetic field already acts back on the turbulence? So we have a strong mean magnetic field, and we assume that it already modifies the velocity fluctuations. For instance, via such an equation, which would be the incompressible momentum balance, for simplicity. But it's not a major complication to add here compressibility, if you want. And I've already...
We're not discussing the kinematic, but the small-scale dynamic.
Not a small-scale dynamo at the moment. I'm still under the assumption that the primary turbulence is purely hydrodynamic.
Which is virtually not the case.
Yeah, I come to this. But the theory needs to divide things simply, and needs to start with the simplest case and to proceed then to the more complicated. Now we still deal with the simple case where the primary turbulence is hydrodynamic. Excuse me, but this is my pathway. So,
since we're asking those dividing questions, is what would, at this stage, I mean the stage before, what would prevent you for doing exactly the same thing for turbulent diffusivity in hydrodynamics? No magnetic field. You introduce a parental mixing length, and you derive the Reynolds stress tensor by saying that UIUJ is some function of mean field profile. Repeat exactly the same thing.
Yeah, I think we could do that.
But it hasn't been tested.
No, I wouldn't like to speak about that today. But we are working on that.
It's not analogous as yet because of the nonlinearity in the momentum equation. The induction equation is a linear function in B.
Yeah. So I've written down this momentum equation already for the small scale, for the fluctuating velocity. And now we have, of course, a UB, so a U by influence of the mean field, which is no longer zero. And so the actual fluctuating U is not identical to the primary one. Or, in other terms, velocity fluctuation becomes a function of B. So what about the consequences of that? Of course, now the magnetic field fluctuations, this BB, which is equal to B in this case, because we have no B0, becomes a nonlinear function of B mean if we consider the things for a fixed forcing. Let us keep the forcing amplitude constant and put in mean fields here at these points with a varying strength. Then, of course, B, and finally, of course, alpha and eta will be nonlinear functionals of the mean fields. And this is just what we see then in terms of quenching functions of these coefficients. But if we change our viewpoint, and this refers to one equation which is not too far away, but it's simply the induction equation for the fluctuating magnetic field. But if we change our viewpoint and consider the magnetic field fluctuations not as functionals of B mean and the forcing, but instead as functionals of the velocities and the mean field. Then we have to concede that this function is still linear and homogeneous in the mean B. A mathematical trick if you want, but I think it's hard to argue against that.
Yeah, if you expect to make calculations numerically rather than analytically, it doesn't matter. If you know this U, it doesn't matter what it difference, right?
Exactly. Because physics should not feel difference whether you, by adjusting the forcing, have created a certain fluctuating U, or if it has been created by the action of the mean field. Nature should not feel this difference. So this is a physical story behind this is a mathematical argument. And the consequence is that we do not have to modify our method. The method as it was established up to now is still valid even in this case. And what we then usually do is that we take the velocity fluctuations from a direct numerical simulation, which is full MHD, which we now from this point on call the main run, and plug it into the test field methods and run this method simultaneously with the main run all the way. So of course the numerical work is considerably inflated because you have not only one test field problem, because there's a series of test fields, you have a multiple of the numerical work. That is true, but the test equations are linear, and this maybe facilitates things again a bit. For an example, let us consider an alpha square dynamo, which is created by having turbulent forcing of the described style, so plane waves which change with randomly changing directions in a box. And if this forcing is appropriately adjusted, then it creates really something like an isotropic and homogeneous turbulence, which is can be adjusted as well to be helical simply by tuning parameters of the forcing. And usually this is done by a forcing which has a almost delta correlation in time, so it's really changing uncorrelated from time step to time step. And periodic boundary conditions. Then we get a pure, in some sense, alpha square dynamo, because to this turbulence, easily a constant alpha scalar alpha coefficient can be assigned, and the solution of an alpha square dynamo is of course a Beltrami field. K equal 1 means the biggest dimension which fits into the computational box. And the property of the Beltrami field is that this modulus is constant and that the current density is parallel to the field. So any curl operation here applied to J or B would do nothing else than put a factor, but would not change the geometry of the field, because it's just the Beltrami property. And further on, these numerical dynamos, which were of course not simulated in the style of a mean field model, but they were directly simulated, nevertheless representing alpha square dynamo, they were driven to saturation, and of course in saturation you have a mean magnetic field which is no longer negligible small, so it needs to have an influence on the turbulence, and the turbulence needs to become an isotropic. There's no way out. That is, for our tensors alpha and eta, we now have to write down something like that. There's an isotropic part which is already there without the mean field, and this is the part, these are the parts created by the influence of the mean field on the turbulence. This is the only possibility to write down these tensors, because we have only one preferred direction. This is the direction of the mean field, and the back reaction on the flow is quadratic. These two ingredients lead unambiguously to these expressions. And here the B hat is the unit vector of the mean field. And yeah, maybe as a side note, you still have an isotropic or a seemingly isotropic relationship between the mean electromotive force and mean magnetic field and current density, with scalars here which are dependent on the modulus of B alone. But this does not mean that the turbulence is isotropic. The turbulence is definitely anisotropic in this case. So the relationship is isotropic. Yeah. One further aspect, because the modulus of B is constant, then these scalars, alpha and eta t, are not dependent on z, what they could be, because in our average means everything could depend on z, but in this case they do not depend on z because they only depend on the modulus, and the modulus is constant for a Beltrami field. Yeah, numerically we have a lot of fluctuations in the game. This is simply expressing the fact that such a sort of forcing is not precisely isotropic, is not precisely homogeneous. It's only up to a certain level, and what is missing up to perfect isotropy, perfect homogeneity, is expressing itself in these fluctuations in Z and T. So,
Matthias, in
yeah.
reality, even here, the only way you've got this is by a Reynolds number becoming greater than critical value for this dynamic.
sorry?
So once you put test field, we always get growing fluctuations here.
Growing.
This is not a case where you do not have small scale dynamic.
It's still the case where we don't have a small scale dynamic. Yeah, but we are still sticking to this assumption that B0 is 0.
No, but when you put the test field,
Yeah.
is this the case where you have alpha square dynamo in the final saturated state?
Is what the case?
Case which I have just discussed.
Yeah.
Right. Even in that case, you had to reach that state, you had to have a supercritical magnetic Reynolds number.
Yeah.
And if you put a test field, it will blow up because the fluctuations will grow because of the small scale dynamo. Isn't it true? Or?
No, I don't think so.
Ask Axel again.
We need to ensure that the Reynolds number is not big enough to create a small scale dynamo.
But it is already big enough, that's why you got this.
I mean, he is talking at the moment only about the fluctuations as a result of imperfect or of finite scale separation. That's all he is talking about. We do indeed see above a certain magnetic Reynolds number the growth of the test fields, but that's test solutions, yeah. But that's not the case you are addressing at this moment.
No.
No, but
because that will really have to do.
Because Axel has to reset every time the test field, the fluctuations. So this case, if you are thinking it doesn't have fluctuations, it's not correct. I mean, it has fluctuations.
Yeah,
and strongly growing fluctuations.
No, not necessarily growing.
I mean, a growth in the test field equation or in the test equation does not necessarily have to do with the small-scale dynamo in the real induction equation, because the test equations, they are not the same equations.
I agree with that. In the real equation, small-scale dynamo is saturated. Okay, that's why you have all this. But you will, okay, I think you should carry on and I'll come back and you have the same problem here also.
Yeah.
You should just carry on.
Okay, so what are results for this model, alpha squared dynamo created by some sort of artificial turbulence? Consider the 1D mean field dynamo model, which you can create by the alpha and eta t values you have stripped out from the test field method. And then we know for such a model that the growth rate has this shape. Kz is the z wave number of the mean field. And we may consider an infinitely extended region or a periodic region. The result will be the same, except for a selection of kz, of possible values of kz. And you get this one for the growth rate, and the growth rate is 0, that is stationary regime, if you have the bracketed expression 0. So now what was done was to check the test field method by calculating for different situations these numbers and checking the expression to be 0 or not. Can I show you the results? It's here for different cases, which are mainly distinct with respect to the magnetic Reynolds number, which you can see from the molecular value of the diffusivity, but changing a lot. So the magnetic Reynolds number was controlled by this parameter, molecular diffusivity. Tilde means only these are dimensionless numbers. And here we have alpha as measured by the test weight method, eta t as measured by the test weight method, molecular value, and the growth rate calculated by this rule, by this expression. Consider the first line. Here we have a clearly non-zero value, negative, but this is correct because the first line corresponds not to a dynamo. This was still subcritical, so there was still a decaying field, and there was a decay rate predicted. All the other cases refer to saturated dynamo, so we should predict by the test group method, by this expression, lambda equal to 0, and what you see here is really, with only one exception, that within the error bars, which comes from the fact that the results are fluctuating, all these predictions are really consistent with the assumption of a vanishing growth rate.
For which k was that? For a number of k?
Or? K equals 1.
The biggest k which fits into the box. Yeah, and this shows the values again as functions of the magnetic Reynolds number. And here I want only to focus onto the fact that both the alpha and the turbulent diffusivity are quenched in the very, at least for high Reynolds number, very similar fashion. So there's only a small difference that there's still over, which really is necessary to compensate for the turbulent diffusivity to get this expression to 0. And sometimes quenching is described by representing alpha as the sum of these two expressions, where one says, okay, this is a kinetic part, it's somehow connected or mainly expressing the properties of the velocity fluctuations which are there primarily for the primary turbulence. And this is expressing the back reaction by use of the fluctuations of the magnetic field. And then, because the sign is different and this part is growing with growing mean magnetic field, you would expect that there is a partly compensation, so that the quenching works by diminishing alpha k by alpha m. And we have plotted here these two quantities, alpha k and alpha m, and they really, if you would do this operation, alpha k plus alpha m, would not result in the quenched alpha value we have measured. So these more or less crude assumption that quenching is accomplished by reducing alpha k by alpha m doesn't seem to work in this situation. Okay, then coming to another application, which is tightly connected with the name of Martin Schrinner, who has done a huge work on that, and in fact about the first application of the test tube method, and maybe it's worth to mention him. Consider an average in axisymmetric geometry, which is again over the azimuth phi, and then you get something like that. All the components of the mean field are only functions of r and theta, and the electromotive force can be represented in this way. This is quite usual, and here you see one part is missing in the derivatives, which is just a derivative over phi, which cannot occur because the mean fields are axisymmetric. And then if one would count that through, we would count here 9, here 9, here again 9 different components, so in total 27 independent coefficients describe the mean electromotive force up to this level only, where we already know that this could be missing because there are no higher spatial derivative, there's no temporal derivative and so on, temporal derivative, but we already need 27 independent coefficients. Note that these tilde quantities have these indices referring to r, theta, and phi, are not real tensors. So that's why I haven't written them, or I've written them only in this component form, not in a compact form. Instead, one could use a covariant form where here really the covariant derivative tensor occurs. And then one could ask for the relationship between these components with the tilde and these tensors. One may rewrite the covariant form in a sort of effect-wise representation. Sorry for this minus. This is simply conventional, so it doesn't mean anything relevant. You might forget about it. But it refers to the pictures of Martin Schrinner, and that's why I've kept This is the UV alpha effect. I haven't even noticed. This is, you know, something sometimes denoted as turbulent pumping or turbulent diamagnetism because it acts like a velocity that transports the mean magnetic field. This is turbulent diffusivity tensor, and this can be related to the omega cross J effect. This has no specific naming and was not really studied extensively. So the tensors alpha and beta are assumed to be symmetric, and K is partly symmetric. And gamma and beta, of course, are vectors.
Good question. The gamma is usually referred to as a velocity, but a velocity field can also have an induction effect, not only a transport effect. Is this by constructing such that gamma cross B is always just a transport?
No. It's exactly the same like a velocity field act. At least the model doesn't restrict that. If it at the end turns out that the gamma doesn't make anything else than transporting field away from the dynamo region, which was so in Martin Schöner's models. Okay, but the model doesn't restrict the action of this gamma to be different from the action of the velocity. At least as far as I know, it does not. Yeah, here we see then, if we would count all these tensors and vectors, 36 coefficients and not 27. This is, we have 9 degrees of freedom, which could be even seen when relating these tilde quantities, which were not tensor components, to real tensor components without the tilde. And you see that if the tilde quantities are given, you can figure out only some combinations of the real covariant tensor components. This is not unique. To make it unique, usually these 3 components were put to 0, which is legal. But the end is, the consequence is that if you represent the result in this form, it is no longer unique again. And for instance, if you see that the beta tensor is not positively finite, it need not to say anything physical, because you can rearrange things by using other assumptions at this place, and you would get another beta tensor, and which could then be positively finite. So the real physical meaning of these effects is no longer that clear, but it is ensured that the result, the mean electromotive forces, is not touched by this ambiguity at this place. Yeah. And 27 coefficients, of course, means 9 test fields, because any test field has 3 components now. Yeah, but this was the original choice of Schöner for the test fields. You see here the number of the test field, and here the 3 components. And you see here, yeah, this is constant, not depending on space, linear in R, and linear in theta, and that's it. And of course, these fields are really nasty, most of them, because, oh sorry, this should be not there, not here. Some of these fields, most of them are not divergence free. They are mostly irregular on the axis, and they don't satisfy any reasonable boundary conditions. And nevertheless, they turned out to be useful for the mean field, for the test field methods. And as applications, I want to mention 2 cases, both valid for thermal convection in a rotating spherical shell, in business approximation, where a lot of geodynamo work has been done in this sort of model, and the results from that have been used for this work. And probably I should skip. Yeah, I should skip a little convection because of time. I go immediately to a geodynamo model where the Rayleigh number was adjusted to be high enough. It is more or less a value which is close to the one in the Earth, which could be realistic. But the Ekman number, of course, is not realistic for the Earth. In that case, it was far away from Earth conditions. Where the Rayleigh number is already 1.8, the critical one for the onset of convection, not of dynamo, but of convection. But it's at the same time already sufficient for dynamo action. One gets then a dynamo which is essentially stationary, except for some rigid body motion. But the amplitude of the geometry even is really stationary. And let us look onto the results. These are maps in meridional planes of all the components of alpha. These are 6 because alpha is a symmetric tensor. 3 components of the gamma vector, and further 3 components of the delta vector, and again 6 components of the diffusion tensor, which now is no longer only beta, but it's beta plus a molecular diffusivity. Nevertheless, you see in D even a negative value, which you would not expect there in the diffusivity tensor, but what I've already said, this tensor is subject to some sort of arbitrariness, and that's why one has not to worry too much about this negative sign. What one sees here in general is surprisingly high level of symmetry of all these coefficients. So they are either symmetric or antisymmetric with respect to the equatorial plane, which was not so clear for all of them from the beginning. But the numerics figured that out. And of course, the crucial test for the test field method is now, of course, and it's done here for just this quasi-steady geodynamo, the comparison between the direct numerical simulation and the mean field dynamo model. So you have figured out all these mean field coefficients, 27, and you put them into an axisymmetric mean field dynamo model, run it, and compare the results with the results of the direct numerical simulation. This is the crux. This is really hard stuff. So it is decided at this point whether it works or not. And here is the comparison. 3 components of the mean magnetic field. This is the growth rate, and we have a saturated dynamo in the direct numerical simulation. The growth rate is 0 because this line corresponds to the direct numerical simulation. This is geometric pattern azimuthally average. So we speak about the mean field as coming from the EMS. The second line corresponds to a mean field model, as I said, constructed by the results of the test field method. And you see here there's a decay rate. So the field is not stationary, it's decaying. The rate seems big, but these are the units. This is the unit of it. And this means, in fact, when comparing to the free decay rate, so this is a small value, it's slowly decaying. And you see there's a high degree of similarity between the geometries, these two geometries, but there are some deviations too. You see, for instance, here, this island is not occurring here. The next line is, for comparison, a model where the coefficients were derived more or less analytically, almost completely analytically, from the velocity field of the direct numerical simulation. These are complicated formulae, but it's possible to be done. And then you get an isotropic results again for alpha and beta and so on, but in the second order correlation approximation. And you see here still a surprisingly high level of similarity. This is an artifact, sorry for that. But the decay rate is now almost twice.
How do you fix the 3 parameter, the correlation time in this case?
It wasn't necessary. Because there's you can derive alpha tensor, for instance, completely without any further assumption from the velocity field from the DNS. If you have a prescribed velocity, if it's completely prescribed in space and time, you don't need any further assumption.
But if I think of the old relation that relates alpha to the helicity or
that's true. But if there in this formula you would employ a completely prescribed velocity, then you would have this correlation time.
Oh, okay.
It's no longer an assumption.
So from a temporal evolution, okay.
Okay. And the last line corresponds to this simple formula you mentioned, in fact, but it's not exactly the helicity here. It's a bit different. Here the vector potential psi of the velocity was used, because this formula corresponds to the low conductivity limit or the limit of stationary regime. Then these are not the most commonly used formulae employing the helicity, but they qualitatively are not so different. And the result is here, and you see that the decay rate is extremely different. So this would not work at all. But this, the third line, the anisotropic Soka, works surprisingly well in some sense. But of course, not as well as the test field method. And summing up what has been learned, I have to hurry a bit. Here you have the phi component of the alpha tensor plotted over the magnetic Reynolds number. This is the Soka result, and this is the result from the test field method, showing clearly that Soka fails from a certain point on, but this point is surprisingly not 1, but something like 10. And this is not, on the other hand, not completely surprising, because we know that the sufficient condition for the validity of Soka is a sufficient condition. Is Rm equal smaller than 1, but this condition is only sufficient. It's maybe not necessary, and we see that it needs not to be necessary. And another story is something could be learned about quenching. This could be done in the model of Martin Schwinner. He could adjust the mean field with help of boundary conditions in the case of magnetoconvection without a dynamo. And here the dependence of the phi component of alpha on SSR number, which is a measure of the magnetic field, first growing and then falling. And this is a ratio of two coefficients, two components, with respect to magnetic field again. And two things are here to be learned. First, B acts not only in the sense of quenching, it may even amplify, and the reason is the relaxation of the geostrophic constraint. Because it's a rapidly rotating system, you have Taylor-Proudman theorem, but if there is a magnetic field which is significantly strong, it relaxes this constraint, and you might get, in fact, get a higher value of alpha, but later on, then the turbulence is suppressed by the magnetic field. And the second thing is, not all the mean field coefficients are quenched in the same way. You see it here, the ratio of two coefficients depends on the mean field itself. And the last thing is something about which of these many coefficients, 27 different coefficients and 5 different tensors or vectors, are really significant. And there was a lot of experiments Martin did, including coefficients and excluding them, and many combinations were tried out. The result is that out of these 27, you need at least 17 to get a good result. The only thing which is really apparently unimportant is this kappa tensor. All the others, even gamma, plays a really important role, and delta too. And we may assess at the end, as a sort of a summary of this axisymmetric method, that such an ansatz containing on the magnetic field and the first derivative with respect to space is clearly not sufficient, because it cannot reproduce a dynamo. It was still a decaying field which was reproduced, not a dynamo field. So higher derivatives were included, and this is technically no problem. It inflates numerical work, but it's not basically a mathematical problem or methodical problem. But the result was not clearly improving the coincidence with the numerical dynamo. So this is an open question.
But yes, with asymptotic series which don't converge, then the general rule of thumb is include as many terms as required to capture the physics you want to describe, right? In this sense, just be reasonable, include as many terms as you feel is necessary.
Sorry, is what?
Include as many terms as you feel is necessary. I
Yeah.
understand that it's not a rigorous statement which you can verbalize.
Yeah.
But, but it's unavoidable. In asymptotic series, it's unavoidable.
Yeah.
Like this.
So it's questionable whether this inclusion of higher derivatives really has sense in this case. We haven't seen that. Martin Schwinner hasn't seen that it really improves the result. So the way out could be to employ a non-local formulation instead.
So you didn't prove the station even where you knew that high derivatives.
Yeah, but how to know that? Of course, the mean field, if you look at it, it may contain higher derivatives to a reasonable extent. So It's hard to judge about that.
But it's a rather strong conclusion to reject the ansatz. Is there a possibility that you might underestimate the alphas, for example, due to finite resolution? Or
I'm not sure. So there were tests with other test fields. The set of test fields was exchanged, and the result was quite similar.
Mm-hmm. And you could get the dynamo?
I mean, this is a fairly complicated geometry here.
Okay.
It was spherical and so forth. I think really higher order derivatives should be there. I mean, we find this in periodic boxes already, as you know. We need higher wave numbers in order to capture what we then call non-locality. And that's, and yeah, Matthias already showed that even in the nonlinear case for periodic boxes, the lambdas then in the end can come out to be exactly zero, suggesting consistency.
Okay,
in simple cases then.
Want to step into that area which is no longer really mathematically as certain, that I went into the wild, because we don't know what will happen to us here. And this means to admit now a magnetic hydrodynamic background turbulence where both the turbulences, both the fluctuating fields, are no longer necessarily zero. And the first question, of course, is does the test field method up to now, which was also possible to be applied in the nonlinear case, that's why quasi-kinematic, is it still valid maybe? And we now had to write down as an evolution equation for this part of B, fluctuating field, which is dependent on the mean field, which reads like that. And ask ourselves whether we could follow the same strategy to say, take something out of a direct numerical simulation, the velocity field, plug it into a test equation, and then you are able, or if you are able to express the result as a homogeneous and linear function of the mean field, then you are fine. Is it possible here? This question arises. And you see it looks fine up to this point, because everything up to this point is linear in BB and employs this velocity fluctuation, which comes from the direct numerical simulation. But at this point, it breaks down because you need something more. The U alone is not sufficient. You need this UB. And another observation is that if you consider the mean electromotive force, again, the first term is fine. It employs the given taken from the DNS velocity and the solution BB, but the second term, which occurs now, is not covered, and we would again need knowledge about its UB.
You may have gone into the wild too fast because...
Pardon?
You may have gone into the wild too fast.
No.
There is a case where there is no Lorentz force.
Pardon?
Suppose there is no Lorentz force in there. You are still in the kinematic regime.
No, if there is no Lorentz force, we are fine. So.
You are not, because you have a small-scale dynamo.
Yeah, you're right. No, you're right. You're
so
right.
I think there is a case in between before you come to this one.
No, the small scale.
Which has to be sorted out, which is not sorted out at present, which we don't know what to do.
So the small scale dynamo is really included. Yeah.
Here it's included, but you have also included the Lorentz force. That's why you are having UB bar, right?
Yeah.
Suppose you did not have the Lorentz force. You still have the kind of...
I mean, that's also included. He is talking about U0 cross B0. And that's part of the left-hand term. Isn't that right?
So
he's talking about...
Here it should be an index
No, it's part
B.
of the right-hand term.
At this place there should be an index B. That is only the part of the mean electromotive force which is depending on the mean field. The mean electromotive force may have a part which is not depending on the mean field, which we are not discussing here.
Yeah, I think it's an illusion because once you put your test field, there will always be an electromotive force which will depend on the test field, which is growing very rapidly.
Sorry, which is where, what?
I think let's discuss it later.
Yeah. Okay. So this is only to demonstrate that the usual method, which we have called quasi-kinematic, would not do the job. And the big challenge is now how to create another method which ensures the property that this part of the mean electromotive force, which comes from the mean field, is still linear and homogeneous in the mean field that is in the test field. Otherwise, if we don't have this property, any test field method would be wrong. So let us consider a simplified model. induction equation as usual, except that this is formulated with the vector potential now, which is not really essential. Then you have here magnetic forcing included for experimental purposes, and here reduced hydrodynamics, where the pressure term and the advective terms are away, but the forcing is still there. And this is, we have no constraints on the velocity, no continuity equation, and the dynamo action is still possible, and we have arbitrary forcing in. And wanted quantities are now, of course, no longer the mean electromotive force alone, but also the mean force, which are expressed here in a general way. In both cases, the parts which depend on the mean field. We will see here 3 contributions, in fact. And yeah, for the mean force, we could again make the same or analogous ansatz like for the mean electromotive force. So a part linear in the field itself, and a part proportional to the derivative tensor. But I won't give any result about that. Let us skip that. And let us now consider, derived from the model problem with this modified hydrodynamics, the equation for the fluctuating fields. It was split up in 2 parts, 2 blocks, the 0 quantities, which are not influenced by the field, by the mean field, and those quantities which are influenced. You see, this first system is completely closed, so it can be solved on its own basis, completely independent from anything else. The forcings go in here, and I've assumed that the forcings themselves do not depend on the mean magnetic field. So they won't occur here at these places. The equations which we get for UB and AB are now those, and they are of course nonlinear because of these couplings here. And everything is still equivalent to the original system. Now, here, in the next step, I have rearranged the quantities a bit. I have at some places used the fact that the total fluctuations are these sums. Of course. Which is not surprising to you. But it was first, on the slide before, this was not used at all, so it was completely split off. Only the splitted quantities were used. And now I have, at some places, employed the total fluctuations again. And you see, here, this place where these fluctuating forces are, and the fluctuating electromotive force, we have, in both cases, for the force and the EMF, 2 possibilities to do that, this rearrangement. They are, up to now, equivalent. And if you now consider this system and regard the velocity fluctuation U and U0, which is the one without mean magnetic field, and B and B0 as given, we might take out U and B from the main run, and U0 and B0 from a separate calculation. If you consider these as given, then this is formally a linear system in these solutions. And it turns out that the mean force and the mean electromotive force at the end is, or are, formally linear and homogeneous in the mean field. And now we are simply doing something very bold and saying, let us take this system and not only say that it is formally linear, but create out of it a really linear system by dropping the connection between these quantities and these. Of course, they are connected. It is written there. But I simply forget about it and say now that they are independent. And this defines me immediately a test field method, which is written here. Again, K indicates the number of the test field. And with respect to the preceding slide, I haven't done anything else than replacing the mean fields by this mean field with the index K, and the solutions by a solution with the index K, which now refers to test cases. And we have to solve the system simultaneously with the main one, with the DNS, and we see we have four different versions to do that, which we can label by the fluctuations from the DNS, which fit into these places here, which define the version. For instance, we take this version and this variant and this variant. We have here a J and here a U, so we name it the JU version. And then we would take this variant and this variant. We have here a B and here a B, and we would name this the BB version. And now it's of course interesting. Let us skip the remarks. What is the result? Again, 1D averages. Then we get this ansatz, which is already known for the mean electromotive force. If we would like to have these coefficients too, we would need in total then 4 test fields again. And again, we applied that for the artificial turbulence, where the forcing is delta correlated in time, isotropic, homogeneous, plane waves having helicity or not helicity. In this case, they have helicity. And we have the following result. Purely magnetic background and kinematics, that is, the mean magnetic field is infinitesimally strong, weak. Sorry?
Did you see your forcing with delta correlation, or is it forcing with Roberts?
Pardon?
Are you forcing with the Roberts flow, or are you forcing with delta correlation?
Sorry, yeah, I was wrong. Sorry. It is Roberts forcing. Delta correlation is the other case I won't speak about. This is Roberts forcing. Sorry for that. No, it's not delta correlation, it's simply regular forcing and giving a regular velocity pattern. And here is compared the Sokka results for this case with the results of the test field method. And remember, this is purely magnetic background turbulence, so a case which is usually not considered. No hydrodynamic background turbulence, only magnetic background turbulence. So any velocity fluctuations come in exclusively by the action of the mean field. And we see first a very good agreement with Sokka where it could be for higher Lundquist numbers, which now takes the place of the magnetic Reynolds number. This is no longer true, but more important, this red curve shows in fact the results of 5 different methods. 4 versions of the new test field method, and the post-field method, which is still applicable here. So they all coincide. And here is something shown for hydromagnetic background turbulence, where both fluctuations already exist, and the mean field is in. It has a significant strength, and we see here a characteristic quenching behavior, where the alpha coefficient goes up very steeply with the magnetic field. And we see 2 different contributions to it, where the one is growing with the field and some sort of devouring the first. And again, here in this case, we have complete agreement between all the 4 versions of the test field method and the post-field method. So surprisingly, because there was no strict or no rigorous mathematical justification for that approach.
So in this, are fluctuations reset to 0 or?
Pardon?
Are there fluctuations when you measure this?
No, not in the case of the Roberts flow. And I was on the wrong rail, but in the case of the Roberts flow, there are no fluctuations. It is simply a stationary pattern, and this is enforced, and there is no need for fluctuations.
So K is equal to 0 here for the test field. K is equal to 0, and therefore this can be done in 2D.
Yeah.
Oh, okay.
Okay, I have to skip all this.
But if you were to do the same thing for spherical turbulence,
Yeah, we have that. Yeah.
one has to check for that. Yeah.
Sure. Yeah. Standard procedure. Yeah.
But for the last slide, I only want to focus on 2 things. What is necessary is a rigorous mathematical justification we don't have. At one place I said I do a very bold thing because I simply forgot about this relationship. And how can this be an equivalent operation? I don't know, but it works. And the second thing, we of course have to extend it to proper hydrodynamics, not sticking to this reduced system where the pressure is missing and the electric terms are missing. And what we equally could do is to apply this bold idea, which is not yet justified, to pure hydrodynamics to figure out Reynolds stresses and then effects which are sometimes called lambda effect and Naka effect and turbulent viscosity, which are altogether surely of importance for modeling the solar dynamo. So, and okay, just over the time.
Okay.
Sorry for that. That's it.
Thank you. Any questions, please?
I'm a bit confused by the 4 test fields methods. Now maybe you can go back to that slide where that was the UD, JD, BV. So these are really 4 sets of equations. And
You see the combinations possible.
where do you get the B0
From a separate run.
That's
From a separate run. You have seen these equations before?
Separate equation, not a separate run.
Yeah.
You solve them all simultaneously.
But simultaneously.
But it's
It's
independent,
in parallel. Yeah. You have the main run, you have in addition these runs, and then you have the the real test field method run in one of the 4 versions, or if you want all 4.
I understood that the U0 and B0 are like prescribed velocity fields that
They are, in the sense, prescribed as they depend exclusively on the forcings.
Oh, okay.
If you prescribe the forcing, you know, in fact, the U0 and A0.
But how do you separate them from the
by
do you do the mean field then?
by solving these equations. And this operation is crucial. You have to take out the fluctuations of that. And here too.
Oh, okay.
You have to do that in your code.
And your assumption is that you can do that separately for the U and the U0 and the B and the B0, and they don't interact.
Yeah, that's true.
So I think the term that Kantor was referring to was this one here. That's of course in the 0 equation included.
Yeah, that's right, but I have a comment to make about that. Actually, it's very nice that one can combine these and make a linear system. So it's very nice.
Over to you.
My worry still would be the following thing, that when you have a large Rn system, although on the average U0 cross B0 will not contribute anything, okay, the fluctuations in U0 cross B0 will grow, correlated with B bar.
Yeah.
Okay, and so we still have to deal with that problem, which we have to still think a little bit.
I mean, the way is to do that is to do the resetting.
That's right.
The thing is, we are interested really in the inhomogeneous linear, in the solutions to the inhomogeneous linear set of equations. And so the part that is doing dynamo activity on this equation again, possibly even modified by this one going, is not of interest. So we can stop the calculations, and if that becomes too inaccurate, as before.
Yes, but what I always worry about actually is that it may be okay for finding out the coefficients with the test field method. But in reality, what's happening is that there is a given field with the fluctuation growing exponentially, at least in the kinematic stage. And then if you have fluctuations growing exponentially correlated with the mean field, then you have all your fluctuating alpha, fluctuating everything.
And exactly that, I think, is a new part which is included. So that's exactly which leads to these B0 terms. These are the new terms here.
No, that UB bar is the part which is influenced by the Lorentz force in the momentum equation. It is not the part which is coming just because of fluctuations.
Yeah, but it's included. That's just this one. This, as you see, is not correlated with the mean field.
That's because the mean is never correlated, but the fluctuations are correlated, as I can write down and I wrote down in the Green's function solution in my talk. The fluctuations are always correlated with the mean. You can write down the equation again.
So let's check whether there's any further questions here, because we are running otherwise.
Yeah, that's fine. We can discuss it.
Yeah. Please.
I was wondering, instead of resetting the test fields, you can also introduce an artificial damping term which works equally well, and I was wondering if that can be motivated in terms of like a minimal tau or something, like damping high correlations by lower order.
I don't think so. Because minimal tau refers to closing, to replacing higher order correlations by the lower order ones, and this would be what we wanted to do, because we want to keep all the correlations.
One could do this a step further, and then
I'm not sure.
I mean, what you could do is introduce something which doesn't affect the final solution. If you can show that, then I think that would be motivation. Then you can motivate that, and it's, I think, something to think more about that.
I mean, in the
I know you have done experiments with that, and they look satisfactory. Yeah, I've not checked it myself, or Petri has not checked it. You should maybe look into that field further.
Because, as you said, in the real magnetic fields, the small-scale dynamo is at some point saturated, but in the test fields, this doesn't happen, right? It will grow at infinitum.
And that's because this is a linear equation. So therefore, we can always have.
But usually, one would expect that the solution of this system are they have a transient process, and then they get stationary because there is an inhomogeneity. And if the inhomogeneity B and J and U is statistically stationary, one would expect that the solutions are statistically stationary too. But we already know that this system has some sort of instability on its own, which is clearly spurious. It's introduced by our boldness. But what we want to have is simply a stationary answer to a stationary input at this place. The test field method relies upon that. If you don't get this stationary answer, you're in trouble.
Any further questions? So in answer to Jean-Francois' question about the last, about applying this, how do you go further? Yes. I think this is good to emphasize again. Sorry. The lambda effect and Anker effect. So the main hurdles that needed to be circumvented or overcome is the nonlinearity in the equations. And by splitting the fields, the fluctuating fields, into two different contributions, one can achieve a linear set of equations. That was proof that it's now possible and can now be applied, of course, to just purely hydrodynamic cases. But the test field is now no longer a V bar, but a U bar.
Right. But then the question was trying to learn from it. There's a good basis when you look at the equations that you've written that trying something like this is a valid method, because indeed you have that equation for U and the equation for B, and they couple through one term. All right. Now the analogy where you go to hydrodynamics would be to write the equation for the vorticity, formally equal to the equation for the magnetic field, and you have the evolution for the velocity, and of course now the difficulty is what is the curl of the other, right? Okay. Now that procedure in hydrodynamics in trying to describe problems in terms of a Prandtl mixing length, in many attempts at fine scale dynamics, has failed miserably. Right? Well, if you don't even get the order of magnitude of the friction on a plane surface, right? Unless you put it like that, right? So people in all these LES refinement and all these, people have devised those K epsilon models to account for the fact that indeed when you get close to what's happening, you have to account for fine grained intermittency and stuff, right? So that method which has been used for a good, I mean, these kind of ideas of writing that the Reynolds tensor is proportional to the derivative of the velocity, which has been used for a while, is not known miserably in hydrodynamics. It would be very interesting, I think, using that very powerful method to try it in hydrodynamics and understand why.
Yeah.
Here there's a basis, there's a beautiful method to do it, and there's some basis on why it should work, as you really explained. And I should, from that, I think one could learn something out of pure hydro.
Yeah, we started the hydro work, but until now we don't know whether the results are correct or not. We have results, but they are not really confirmed. So, and that's why I don't want to speak about that.
No, it's a harder problem. It would be very interesting because it is a powerful method, and learning how it fails in the case where it is known it will fail, will be very interesting to know where the subgrid modeling has to take place, at which scale. When you do, especially the harmonic method, is beautiful.
There's a step, of course, between going from such mean fields, which are over a large length scale, typically, to a subgrid scale modeling. We all of a sudden are interested in so-called mean fields, which show a lot of variability. So it probably is quite analogous, but it's
it would be analogous. It's compared to DNS, apply it to it, take only the terms that are to come of that spectrum in K that you can get, and see where it goes wrong and why. You know, if you could provide a self-regulation mechanism for people that do adaptive measure finance, stuff like that, would be fantastic. To know where it is that when you account simply for macroscopic diffusion, you don't do it right.
Okay. Is there any further question? So we have the opportunity to talk to four of the lecturers. And you have the plan. It's again as usual on the web. And here's the page. So the first group is Anvo's group. They will meet in the large seminar room of House 12, the Astro building. Jean-Francois as well will be in the Astro building in the first round. Matthias will be in the small seminar room of the Norwegian main building. And Petri in the large seminar room of the main building. And then after that we swap in a familiar fashion. First, large and small within each building will be swapped, like this. And then after that, swapping buildings, but staying in large. So that means Jean-Francois will go from the large seminar room in House 12 to the large seminar room in House 13, and likewise for the others. Okay.
We change like last time, like Monday. Was ist zufrieden?
Ich glaube ja. War gut.
Ja, die Zeit war sicher zu knapp. Aber das ist manche Erfahrung mit so langen Fotos.
Ja, das ist immer.